Cast is now starting. All attendees are in listen-only mode.
Okay, well, good day. Welcome everybody to IEAGHG webinar on enabling industrial CCS clusters. Quick introduction to ourselves, the IEA Greenhouse Gas R&D Programme. We're part of the IEA's family of technology collaboration programs since 1991. We have 33 members from 18 countries plus OPEC, EU and the CIAB. And our members help us set the strategic direction and the technical program, and we are a technical-based organisation. We don't define policy. We're not advocates of any one particular technology. Okay, next slide, please. So apologies for the delay. The remote clicker that worked fine seconds ago is now not working. So what we do, this is what we do, look at mitigation options of greenhouse gases, focus on R&D and D of CCS, technologies, carbon capture and storage technologies in particular. And we follow developments in capture technologies, in geological storage, and everything in between, and non-technical issues as well. And our objective is to provide our members with independent technical evidence base, and also to provide a policy audience with an independent technical evidence base as well. And in that way, we engage actively with the Carbon Sequestration Leadership Forum, for example, with the UNFCCC, with the ISO, and with the IMO, and other relevant regulatory bodies. We're able to do this because of our members. Thank you very much to our 33 members. And also, I should mention our conference, GHGT 14, that's going to be in October this year. Thank you very much to everybody who submitted abstracts. An excellent number of abstracts exceeding the last GHGT conference. And thank you very much to all of the reviewers, all the 140 of you, for the excellent reviews you've done on the abstracts as well. So I'd like to introduce our speaker today. This is Dr. Yasmin Kemper, who's a key member of our team here. Yasmin is a senior technology analyst. She's in the capture and integrated systems team, but actually she covers a broader area than that. She covers in particular bio-CCS, or BECCS, which is quite famous now as an independent expert in that area, but also issues around LCA, utilization of CO2, CO2 accounting, and also hubs and clusters and work around that. So Yasmin will present to you for about 30 minutes. And as she's presenting, you do have a facility on the webinar to send us your questions. So please do that if you have any questions, and we'll try and pick those up. And there'll be time at the end for Yasmin to answer those. And any that we don't have time for, we will follow up by email afterwards. So with that, I'll hand over to you, Yasmin. Thank you very much.
Yeah, thank you very much, Tim, for the kind introduction. Hello again, my name is Yasmin from IEAGHG, and today I want to present to you our recent work that we did on CCS clusters. So the title of today's webinar is about enabling specifically industrial CCS clusters. And I will first give a short introduction, and then I will talk about our first report that we did in 2015 on CCS cluster projects, and we did a review of existing clusters, but also we looked at where future cluster opportunities globally could be. And after that, I will talk about our more recent report that's been just published a couple of days ago, and that is a study on enabling the deployment of industrial CCS clusters. So I have put in the link here for you, and you can download both of these reports on our website. So if you are further interested in the topic or want to have some further information, which we can't today go through in detail, then you're of course happy to download those reports from our website. So the deployment of CCS in energy-intensive industries is quite vital to meet our current climate mitigation targets economically. And industrial CCS clusters can also play an important role in preventing so-called carbon leakage. This is, for example, energy or emissions-intensive industries just relocating elsewhere where there are no emissions reduction measures in place. And if you look at those, especially industrial CCS clusters, you can also quickly make out that they might have different needs and challenges in their deployment compared to those clusters or point-to-point projects that only involve power generation. So that's why in 2015 we did a technical report, and one conclusion from that report was to further investigate also the financial instruments and forms of contract for those clusters, and especially those involving energy-intensive industries. So this report in 2050 was done by Cofrid Technology, and the author was Mike Haynes. And just to mention, Mike Haynes was a former IEAGHG member, and so he reviewed the existing clusters at that time. And in this graphic, you can see certain clusters and their capacity in megatons per annum of CO2. And you can also see that they differ quite a lot in what CO2 would be available from those clusters. And you can also see that, for example, for the US, there is already a very large amount of naturally occurring CO2, and also some CO2 that's separated from natural gas. And you can also see from, if you just look at for example, the Yorkshire-Humber clusters, that a lot of the projects have a kind of phased approach, and that they kind of build up their capacity through the project. Some of those clusters also tend to have a first anchor project in order to mitigate financial risks. And you might also then notice that they are quite different, so it's not so easy to draw any firm conclusions from those patterns. And yeah, we did a study in advance of the studies just on CO2 pipeline infrastructure. And there we already saw that hubs and clusters, they don't seem to have any specific set of rules. And so each system or each cluster might have its own standards and requirements. And yeah, the study then went on to look at what is the maturity of the business cases for those clusters. And all those elements were assessed separately and based on their stage of development. And you can here see the elements that, or the breakdown into which we considered the assessment of those clusters. So some of them, like the blue color, would be they might have a blue sky idea or didn't even put anything forward on how the business case could look like. And then the red color said that mobilization has already started and is close to completion. The yellow color used for the different where you're already in a kind of understanding or design phase, and then the green color more something like a traffic light system. Green, you're almost good to go. You have maybe implemented the business case and also arrived at a mature business case plan. And if you want to have an overview of the full approach of how we collected and analyzed that business case information, then that's explained in detail in the appendix of the report. And then where possible, that means where enough data was available, we then tried to map those business case elements. And I've here taken two examples from the study. One is the Rotterdam cluster at the top, and then below that the Alberta CO2 trunk line. And you can see here from the mapping, like key partners, key activities, key resources, value proposition, customer relationships, revenue streams, and cost structure. That for example, those two clusters are in kind of a very different phase. So there has been done like some preliminary mobilization for the Rotterdam cluster at that time, and the Alberta trunk line was already much further ahead in setting up the business case. We then went on to look at what could future or where could future CCS clusters be. And we found out that they could be, for example, prime locations in countries with mature oil producing areas, also countries that have significant gas reserves, or where there is a significantly cheap feedstock available for gasification or other industrial processes. Also where you already have sharing resources in place, for example, for CCS elements, the capture, transport, and storage infrastructure. Also places where government funding is available, so that could enhance the implementation of CCS clusters. And also where you might have international cross-investment opportunities. And also where you might have other long-term funding available for those clusters. And maybe to name some examples, some of those regions would include parts of Mexico, Indonesia, some oil-producing regions in Russia, some places in the former Soviet Union, and also in China. So to summarize the conclusions from this first report that we did on the review of the CCS clusters, we found that the most successful cluster projects are based on CO2 EOR and thus are in the United States. The cost reduction by combining infrastructure, for example, for CO2 pipeline and other pooling services is important. Long-term funding required to maintain momentum in the project and also to retain the key staff members was also pointed out as very crucial, because the problem is sometimes that you have projects and you acquire a lot of knowledge, you have people working on it, and then for some reason the project does not go ahead, and then all the knowledge kind of disperses in some cases, and also maybe people are kind of willing then to change the industry and work in other fields, and so some of their so-called gray knowledge might get lost. Also, that a good CCS cluster location should be in the position to attract funding, especially international funding. And as we looked into first a review of where the clusters are, where the clusters could be, and that short assessment of the business case maturity of the existing clusters, we found that a lot more work is needed on the development of funding mechanisms and also for international investment. So those conclusions then led us on to commission another study, and that is our most recent study on enabling the deployment of industrial CCS clusters. And we commissioned this work to Element Energy, and the authors for this report were Emra and Elian from Element Energy. And the scope for this work included to define the technical and commercial risks and incentives associated with each main element of the general CCS chain. And that would include a high-level analysis of the commercial risks associated with CCS, also a definition of the interface risks associated with each step of the CCS chain, and also to identify the type of entity best able to manage each of those steps. Then to go on and explore differences and commonalities of CCS clusters based on power generation, and also the differences for energy-intensive industries. And for that, we concentrated on 4 different models, and the models were set up with the help of what other studies and reports were already available in literature. So we chose the first one where we have a public transport and storage company, a second one where TNS are run as regulated assets. Then a third one where we have an anchor CCS project with third-party access. And then the fourth case would be a case based on a cluster on CO2 EOR. So after setting up those models, we would then wanted to go into investigate the management of counterparty and default risks in the light of maybe a different profile of the energy-intensive industries compared to power generators. And then to look at whether we could develop or suggest investment mechanisms to overcome the lack of benefit of CCS to energy-intensive industries, and also to evaluate things like risk allocation, third-party access options, and what models of ownership, maybe both public and private, would be suitable for running those ICCS clusters. Then the geographical scope we looked at was North America, Europe, China, and Australia. And we then assessed whether one or maybe all of those models we looked at would be applicable in those regions. So this is a slide that shows you the illustrative ICCS cluster that we chose as our so-called base case. The total cluster emissions are 5 million tons per annum. And you can see that you have industrial companies from different sectors. So we have a hydrogen plant with 0.3 megatons per annum. We have an ammonia plant with 0.4 megatons per annum, a refinery with 1.1 megatons, a steel plant with 2.5, and a cement factory with 0.7 megatons per year. You can see that for the onshore CO2 transport, we have a trunk pipeline that's 50 kilometers long, and it's sized as 10 megatons per annum. So you can see it's 2 times oversized. And then you have smaller feeder pipelines, which are up to 20 kilometers and just about the right size to deal with the emissions from the emitter. And we transport high purity CO2 at 100 bar. Then we have a shoreline hub, and from the shoreline hub we have the offshore CO2 pipeline, which is 300 kilometers long, also 2 times oversized, and has a pressure of 150. Which then leads to our storage reservoir, which is a saline aquifer with an injectivity of those 5 million tons per year, and it has a total storage capacity of at least 150 million tons. So we then investigated or had a look at our model number 1, which was that we have a public T&S company. So the government owns and operates the transport and storage infrastructure and fully funds it through a public company. And all transport and storage risks are held by this company. And you also have an independent regulator. And then between the industrial cluster and the public T&S company, you have an offtake agreement, and you also have the regulated transport and storage fees. And the government provides storage and loan guarantees, and also industry-specific incentives and grants, which cover 20% of the capex of the CCS cluster. And in our analysis, we run. I'm not going to show all of them today. We run the cash flows for the models, and we found that this is one of the lowest possible costs of finance that you can arrive at. And it's also the least cost option for new TNS if it's politically acceptable. Then we looked at model number 2, which is transport and storage as a regulated asset. And here, as I said, TNS is operated through a regulated asset-based model. It allows somehow higher returns than model number 1. And 50% of the TNS revenue comes from capacity payments. And a positive thing about this model is that asset regulation is likely viable in all the regions that we were looking at. So yeah, you can see here that the government again provides storage and loan guarantees, and also the grants that cover 20% of the capex towards the industrial cluster. But it also provides capacity payment grants to cover stock characterization, volume guarantees, and a cap on long-term liability to the storage and the transport parts. And between the cluster and the transport and the storage, you have again regulated transport and storage fees, and also offtake agreements. Model number 3 was the anchor with a third-party access. And here the anchor absorbs all costs, including the infrastructure oversizing, and only marginal costs are recharged. And we found that this is the best case scenario for a third-party access case, and that it also might be the least cost solution for permanent CO2 storage, apart from model number 1. And in this model, the government owns and operates the TNS infrastructure, and it provides again the storage and loan guarantees, and also the industry-specific incentive and grants to the industrial cluster. But what we did not include, or what was out of scope, was the incentives for the anchor project. And between the existing emitter and the existing infrastructure, you have again the transport and storage fees and the offtake agreements, but you also have those setups between the new joining emitters and the existing infrastructure. And model number 4 was the CO2 EUR case. And for this case, we assume that the entire CO2 is sold to the EUR operator at 20 pounds per ton. And what's important in this model is that there might be a conflict of minimizing versus maximizing injected CO2. So from the operator's point of view, you might want to minimize because you're paying for the CO2, but from the kind of climate change and CO2 storage perspective, you might want to maximize how much CO2 you're storing. And for this case, additional regulations and tax incentives could likely be necessary depending on the location. And one important message that we found is, and we will see that in one of the slides later in numbers, is that the revenues from CO2 are reduced, but they do not eliminate the need for subsidies. So we then compared those 4 business models. So Element Energy calculated cash flow for all 4 models. And we assumed that government will de-risk the project by providing storage guarantees to the emitters, volume guarantees to the TNS company, and also loan guarantees if the debt service coverage ratio is below 1. And that was one that we intensively discussed with some of the stakeholders, how this threshold of DSCR should be, and also by providing capital grants. There will also be comprehensive offtake agreements in place, and as I showed you on the first slide, we assume that the pipeline network is oversized to make it easier for future projects to join the cluster. So, and this is one of the main results slides that we got out of this exercise. So you can see here both the levelized cost of abatement and also the levelized revenues for the 4 models in pounds per ton of CO2. And you can see, if you look at the left side on the levelized cost of abatement, that if you look at the first red chunk of the bars, that the capex and the opex for capture are the same. And what makes the difference is really the transport and storage fees. And here you can also see it in numbers that CO2 ERR is a great help in reducing those costs. It has the lowest levelized cost of abatement of all 4 models, but you also see that there is no full offset. You also see that the model number 3, the existing TNS infrastructure with the Anchor project, is one of the low-cost options. And it also, if you compare model number 1 and 2, which is public TNS company versus private TNS company, that the public TNS seems to be more cost-effective than the private TNS company setup. We then looked at risk assessment, and we came up with mainly 3 main risks that we wanted to look at. The first one is a storage failure that would lead to a 3-year delay of the project. The permanent reduction in TNS availability to 80%, and also that consumer demand in the respective industries decreases by 2% per year, which would affect the emissions profile. And you can see here clearly from the numbers in that table that show the emitters NPV loss and the TNS NPV loss, and also the increase in government's levelized costs that they would need to provide to subsidize the cluster, that unmitigated risk could easily lead to a bankruptcy of the affected parties. And you also see that, or might conclude that for each case you would need to make a very detailed risk assessment, and the outcomes apparently, of course, depend on the location of the clusters and all the detailed setups of the business case and financing. And also that it's very important to find a right balance between necessary and excessive government guarantees. So that's a very fine line to operate on. Of course, we want the government to incentivize industrial decarbonization, but we also should be very careful not to put all the risks and all the burdens and all the costs on the government. This slide just summarizes some of the key risks and how you can mitigate them. And the key risks that we identified in the studies were an uncapped CO2 storage liability, emitter default volume, or a storage failure or non-availability of the storage reservoir, and also a default on loan repayment. And at last, an emitter final investment decision failure. So you can see from the right side that a lot of those risks can be mitigated by guarantees, which are either volume, storage, or loan guarantees, also by grants, and also by some backup, for example, having a backup storage reservoir that you can rely on if it should prove that your first storage reservoir is unsuitable, and also by layered insurance approaches. We then looked at how the models would apply to the different regions, and if we look at North America, the US and Canada, there we found that some future ICCS clusters will likely join already existing networks, and that especially in the short term, the CO2 is likely to be used for EUR, because that's how it is set up now. And taking those first 2 points in mind, it's quite likely that a combination of models number 3 and 4 will be viable. So that's number 3 was an Anchor or a CCS project. Number 4 was the CO2 EUR model. And also in the US, the subsidies can be provided by measures such as the 45Q tax credit. We then looked at how it could be in Europe, and we found that Model 1 broadly reflects what the current activities and intentions are, for example, in Norway and in the UK. And that model number 2 would be preferable for governments that are not interested in getting too much involved with transport and storage. We found that the applicability of model 4, the CO2-UR model, is quite restricted, as the CO2-UR opportunities are currently quite limited in Europe. And also that the subsidy type in Europe will likely be a kind of contract for difference that's based on the EU ETS. When we assessed the situation in China, we found that there are currently no CCS specific incentives, but some of you might know that a national cap and trade system is underway and is currently being designed and tested. And from this perspective, model number 2 looks promising, but it might not be the best option for all provinces. I mean, China is not totally homogeneous, so each province might have a different approach. And although maybe overall one model looks suitable to most places, there will be definitely differences in the regions, so you might need to choose a different model. And what you might also want to do is considering hybrids of models. So a hybrid of model number 4, the CO2-UR, and number 1 might find a high rate of applicability and feasibility. And finally, looking at Australia, if CCS in Australia is deployed in the power sector first, then of course model 3 with the Anchor CCS project is likely to be a prime candidate. And if you look at the other models, maybe model number 2 is likely more suitable than number 1, as the government is maybe more likely to take regulatory control. And at the moment, there are also no CCS-specific incentives. But what might be employed in the future might be contract for differences, certificates, or maybe feed-in tariffs to improve the situation. So the conclusions from this more recent assessment on the, especially on the financial setups, and included that guarantees on launch, storage, and CO2 volumes are key prerequisites for investment. We found that the costs for the government are somewhere, depending on the model that you choose, between £29 and £53 per ton of CO2 abated. One thing I didn't go into too much detail here is that we looked at the jobs, and ICCS can clearly play a role in preserving local jobs and industries. I want to be a bit careful with that finding, because of course you can always say, if we are not preserving the local jobs, there might be new jobs in other sectors to emerge, so that might kind of be things that outweigh themselves. But for existing industries, it's definitely important. And we investigated models that are relevant in all the focus areas we looked at, which are North America, Europe, China, and Australia. And sorry for jumping back to the slide. We found that the ICCS is by no means yet commercially mature, and that the 4 key enablers that exist are to mitigate the risk of carbon leakage, to provide emitters with margin certainty through subsidies. We found it quite interesting and maybe a bit counterintuitive, because we always talk about whole chain assessment and whole chain integration. What we found from our results in this study, that it might be very important to decouple the business cases for capture and the transport and storage infrastructure. And very important to share key risk with the government through guarantees. And the third point here, which we have, I think, seen in the figures, the required level of government support is quite high. So government will play an important role in enabling those CCS clusters. So with this, I would like to close the presentation and thank you for your attention. And if you have any questions, you can either ask us now, or we can reply to more detailed questions by email.
Okay. Right. Thank you very much, Yasmin. Thank you for that interesting presentation and summary of those two quite detailed reports. One quick question is on the second report, you mentioned the input of stakeholders. So
Yes.
which stakeholders or what types of stakeholders did you get input from on that?
We had a very large a group of stakeholders that Element Energy were able to put on board. So firstly, we were supported by two financial experts, Richard Simon Lewis, who led the financing, structuring, and capital raising for the White Rose CCS project, and also by Angela Whelan, who helped establish the UK CCS Commercial Development Group, which she led for the last couple of years. So we had direct input from those experts, and we also contacted a full list of other experts from BES and also from financing industries such as Société Générale, also from Gaznova. We had a lot of input from Norway. We had input from the European Investment Bank, from the Tees Valley Combined Authority, because apparently they are quite occupied at the moment in setting the Teesside cluster up. And also we had input from Natural Resources Canada, the Ministry of Petroleum and Energy, also of course the US Department of Energy, CO2 CRC in Australia, and also from the International Carbon Capture and Storage Knowledge Center in Regina. So we had quite a broad spectrum. We tried to cover all the parts of the chain and all the locations that we looked at.
Very good. Thank you, Yasmin. Just to clarify something, you mentioned carbon leakage in one of the slides. You've got to just explain what you mean by carbon leakage.
I think I shortly explained it, but more or less we mean that if you have an emitter in a region where you, for example, have a high carbon price, it is always the risk that this emitter, once the carbon price is imposed, will just move or relocate its business to somewhere else where there are no regulations in place and where he doesn't have to pay the price for emitting his CO2.
Okay, thank you, Yasmin. So we've got two questions which are very similar and relate to what's the best metric to use to compare different ICCS projects? And somebody's given examples of jobs, health, and economic aspects as well.
Yeah.
So that's a very simple question, but quite a hard question.
Yeah, I think it's a hard question to answer because apparently you have all of those different things, and some of them we maybe not easily put a monetary or comparative value on, such as health and jobs and what is the best metric? Well, it's hard. It also always depends on the perspective that you look at, because if you try to develop a CCS cluster somewhere, apparently the people who already work at the industrial plant will have a different perspective or different best metric, what it's best than, for example, the operator or the government or the local council, and also the people that are living there. They all have different interests, and I think it's hard to find a metric that can, of course, in our times, an important metric is always the costs. So the cost of abatement, especially if you look at climate change.
Okay, that's a hard question, but it's a good hard question. A good question,
which I think there is no 100% right or wrong answer.
And I think at the GHGT conference, I think we're going to see some work being presented there on the employment metrics associated with CCS. So the more we gain knowledge on that area, the better. But obviously, as you say, it's very
Yeah.
specific and project specific and industry sector specific as well.
Yeah, it always depends what industrial sectors are represented in your cluster.
Yeah. Okay. Yeah. So is that all the questions you saw up there? Okay. If that's all the questions that we've got in, thank you very much, Yasmin, for that.
You're welcome.
Summary of those two detailed reports.
Yeah, and apparently much more information is in the report. I mean, we didn't have time today. We looked in the report in much more detail into all the cash flows for the different industries as a breakdown. So if you are more interested on what effect this will have on one industrial emitter from a certain industry, it's very worth to just check the report. Yeah. Because it's all in there.
And it would be interesting to revisit this work as well, because we're seeing the cluster development progressing in Norway in particular at the moment. And they're doing their own economic analysis.
Yeah, we had lots of recommendations on how could we go on with this topic, what could we study in more detail, and we will consider that and think about doing some follow-up work maybe on this topic.
I suspect that's people wanting to gain some learnings from those projects, cluster projects that are being developed.
Yeah.
I mean, in general, the government support in such projects enables the sharing of information and results out into the public, like the UK government did with the UK projects very well through the feed studies. So maybe we can hope to see similar from the Norwegian projects, but we could certainly run this study again and put more up-to-date or more valid data, more specific data in, and even look at other regions as well. Interesting, those 4 regions that were chosen. So with that, I think that was all the questions. Just to draw to an end, to remind, I've mentioned the GHGT 14 twice so far. I'm going to mention it 3 times because the early bird registration is open now. And I think the early bird date is until
13th of June.
13th of June. So if you're interested in attending, we've got over 1,070 abstracts in. There will be 350 oral presentations. There will be many hundreds of poster presentations. There's going to be a lot of good work presented and shared and discussed there. So I urge you to take advantage of the early bird registration and register before the 13th of June. And with that, thank you very much for listening to our webinar. I hope you've learned something from it. The reports are available on our website. And if you have any follow-on questions, then please email us. Thank you very much.